This talk is kind of different to what I've been doing in the last few years at sambaXP and other conferences. I focused mainly on SMB and on Samba. And this talk is now about the other side of file sharing protocol that is widely used, which is NFS. Why is this talk happening now? Actually, somebody asked me to deeply look at some common infrastructure to get SMB and NFS locking done right in an interoperable way. So do I have to let Tom in? Okay, Zoom just popped up and I will ignore these, please. Somebody entered the waiting room. So somebody wanted me to look at how interoperable locking between SMB and NFS could work. And so I had to dive deep into the NFS RFCs and all the documentation around this. And this is my talk on SMB and NFS compared. Okay, what do we have? We have file sharing protocols, and we have different access paths to file systems. And in our world, or in my world at least, it's basically directories and files that live on a POSIX file system. And I'm working on Samba, obviously, and this gives external access to these directories and files. And obviously, there's also NFS servers, both the KNFSD and Ganesha and possibly others. These three walls have different requirements, slightly different requirements. In the end, it's all directories and files, but they come from different historic backgrounds. If you look at what POSIX does is, you could, for example, call the kernel a server. I'm coming from protocol world with servers and clients. If you look at the server in the POSIX side, POSIX immediately notices when the server dies. Everything is gone. The server has crashed. When the client dies, the server immediately knows. So many of the problems that POSIX, that NFS and SMB have to deal with just don't exist. In particular, what happens if a client reboots, if a client connection goes away? POSIX doesn't as much have to deal with caching between client and server, between kernel and user space process, because the latency between user space and kernel space is much, much, much smaller than if you go over a network. And yeah, so when you now enter SMB and NFS, there's a little article on Wikipedia on the fallacies of distributed computing. Essentially, everything between client and server is really, really slow. And either side or everything in between, in particular the network, can fail or even give wrong results. And this is something that NFS and SMB both have to deal with. And they do it slightly differently in different aspects. And this is something I will come to. So what does interoperability mean in this context? If somebody opens a local file or creates a local file with Linux semantics, yeah, we have our well-known semantics. The Linux NFS servers have to map these semantics to what the NFS protocol does. One example where NFS and the local file system kind of differ is what happens when you delete a file. For POSIX, if you remove a file that is still open, the file is still accessible as long as anybody having that file open lives. So the last process that actually closes a file will make the file contents go away. And the Linux NFS server has to map this POSIX behavior to the NFS protocol. And so if something in the NFS world just removes a file, you will many times see these little .nfs removed something file names that try to simulate what this behavior in POSIX does. And the same happens with SMB. There's also a different kind of semantics when removing a file. Over SMB, you can't really remove a file. You open a file for deletion, you tell it to be removed, and then if you close the file, then it's actually gone. But in between you telling the server, please remove that file, and closing it, it will still be in the namespace, different to a local POSIX file system. It will still be in the namespace, but you can't access it anymore. And yeah, there's other protocols. S3 also has to live in the same space. S3 has its own concept of directories and files. They completely look different, but I mean, it's also talking about data that have names. If we now look at just the SMB, just the NFS, just the S3 protocols, the free software world solves these mapping problems that, for example, file deletion looks a bit different in these protocols pretty well, I guess. So we have Samba, we have the kernel SMBD, we have a couple of kernel NFS servers, we have a lot of S3 servers. So they solve the mapping problem between POSIX and what the protocols require pretty well. However, if we want to talk both protocols in this talk here, like NFS and SMB, the story becomes much worse. So nobody really has ever addressed the interoperable locking, for example. And what happens if a client over SMB opens a file with not sharing anything, like file share delete, file share write, file share read, not allowed? How is NFS supposed to behave? And nobody really thought about this yet in the free software world. Famous last words. How hard can it be? Yes, it is hard. Why? If you just look at POSIX, even that being a seemingly pretty simple API has its subtleties. For example, if you want to make sure that a file is actually stable on disk, you have to play a dance with fsync, fdatasync, and so on. And if you create a file, how do you make sure that it's actually on disk, fsync on the directory, and so on? But the basic semantics, being a local file system, are simpler than I would think, or I would see the NFS and SMB protocols, and they are pretty well known. On the other hand, SMB and NFS are really, really complex. SMB is several thousand pages, I would guess. The NFS, the NFS 4.1 RFC is 560 pages. I actually printed that out, but I would guess that there are other documents that are referenced by this, and so they are complex. I have been living in the SMB world for almost 30 years, or even more than 30 years now, and understanding SMB, I don't understand every corner of SMB, or I, from time to time, have to ask Metze or others, how does this actually work? So these protocols are really complex for a single developer to understand. And if you really want to make them interoperate with each other, it takes somebody to understand both. And so why has this never been done? So if from Samba and SerNet perspective, nobody cared enough to actually pay us for doing this. So and maybe in the NFS world, there is this old history that says over NFS locking doesn't work. And so maybe this is either true, or it is sufficiently understood in the NFS community that most users who could care, who could benefit, just don't care. And they don't rely on locking at all. They do all their locking requirements with external protocols like some kind of queuing system or so. So possibly this is just not as important a problem that somebody would really, really have somebody else take a deep dive. I'm hoping to shed some light on the differences here, so just to get the discussion started. So where do both protocols, and from my point of view, differ here? First is security. The NFS security, as I'm seeing it in practice, is usually machine-based. And most of the NFS deployments that I see, you could actually translate NFS with no file security because they are non-encrypted, they are non-authenticated, they just rely on the client to get the UIDs and GIDs right. SMB, by default, all sessions are user-based. So the security is based on a user typing in his password or coming in with a Kerberos ticket, and all the security is per user. A user could also be the machine itself, but essentially most of the security is based on users. Then we have difference in ACLs, access control lists. There are file name semantics that slightly differ. Both protocols can do, from a protocol perspective, can do case sensitive and case insensitive. SMB has some special file name characters, but these problems are, I would say, shallow. They are not really deep and difficult to solve. Then if you look at directory, file and directory metadata, both protocols from a protocol perspective are very, very similar. They differ in slight details, but in general, they are pretty much the same. Then comes the topic of request replay. What is this? One of these fallacies of distributed computing is clients can fail, or servers can fail. What happens, or network connections can fail? What happens if a client decides this request that I've sent has not arrived? It could be that the request hasn't arrived. It could also be that the response hasn't arrived. How do we deal with this? Both protocols differ significantly here. And also locking and byte range locks are slightly different. And client caching, that's another topic that I will come to. So security. SMB had password protections from day one. I looked up the core protocol specification. Even in the tree connect, there was a password-based tree connect for share security. So even in the core protocol in the 80s, you could have passwords. With the Landman 1 flavor of the protocol, Microsoft or whoever added a session setup request, which means that a user can actually log in, and this user can then be given rights or distinguished from other user server side. The scope of a security context back then was the transport connection. I mean, they have fixed this with multi-channel and the concept of a session and session reconnect in later versions. But essentially, the scope of this security context is always the transport connection that is signed, sealed, encrypted, and so on. NFS, however, relies on underlying ONC RPC mechanisms for security. And this is where this 16 groups per user limit comes from. ONC for RPC, for example, has a hard limit in the authentication headers that allow only 16 groups for a single user ID, and for the auth-sys or auth-unix flavor of authentication. This is the no file security. Let's rely on the client. When you look at the NFSv4 RFCs, with NFSv4 RPC security via GSS API is a requirement, even with very specific mechanisms. 4.1 lifted that a bit, but the point is with NFSv4, you have to support, if you have a server and client, you have to support RPC-SEC GSS with transport security. However, in SMB, the security context is always the transport connection. Not so with NFS. Here we have the security context always on the individual request. Of course, the security context representing a user will be longer lived, but you can decide on a request by request basis, do I want to encrypt or sign or seal or whatever security context do I want to use for this particular RPC request at a very low level? And NFS even allows to ask for different RPC security settings per file. It can say, hey, this file is super secure. You are coming in unencrypted, not allowed, use encryption for this file. And from there, for this directory, all subdirectories or so. This is something that I don't believe SMB can do. As NFS still has to live with unprotected RPC, and NFSv4 introduced some logging state, they have to protect against Volker destroying Ralph's logging state. And this in a separate way had to be protected with some sort of authentication. So NFS decided not to fully rely on, hey, we are transport protected with a user session always when doing logging. They had to live with the fact that most of the installations don't run with any security, but still you wanted logging to work. So they invented a separate security mechanism just for the logging calls or logging state, which is kind of weird to me, but yeah, this is NFS. So coming to ACLs, SMB has ACLs defined essentially by the Windows security model and the NTFS model. The principles that you can give privileges or rights or deny rights are security identifiers S1 521-something. These security identifiers don't have a type. You can't, from just looking at a SID, tell this is a user, a group, a machine, and so on. They're just anonymous blobs, essentially, that you can assign privileges. You have 13 bits granting or denying specific access, specific type of access on the individual objects. NFS up to version 4, before version 4, basically only deals with the POSIX permission bits, RWX, and so on. NFSv4 adds the 13 bits from the Windows documentation, plus even 2 more. So we have 15 bits that we can individually set on an ACL. NFSv4.1 adds ACL inheritance flags, and what you can see is also the concept of a system ACL and deny ACEs are supported. Deny ACEs are the one aspect, if I remember the discussion correctly, that block the Linux kernel from accepting NFSv4 ACLs. There are strong forces in the Linux community to not allow deny ACEs. And so this is why in the Linux community, we don't have NFSv4 ACLs yet. But what you can see from this is that the NFS community, and in several places in the RFCs, they even state this explicitly, this is done to accommodate Windows clients. However, this is not really complete. In the NFS protocol, you can see that you have an access call. I can ask for, if I was to open this file, what could I do with the resulting handle? And this call only supports 6 out of the 15 bits. So I can't arbitrarily ask for anything that I can set on the ACL with some of these calls. To be honest, I haven't looked at the open call, but I would guess that I can't really map what Windows does with the create file call, where I can individually really set all these 13 bits and get access allowed or denied. And from then on, I can just do what I've been asking for if I was granted. If you look at the ACE principles, the SIDs in Windows speak, these principles are full UTF-8 strings. I mean, probably some length limitations, but the protocol, in the protocol, it's just a string. In whatever protocols were there before NFSv4, it was just UIDs, GIDs, so 32-bit IDs. But NFS made that UTF-8 strings. And the standard is that you have user at domain. But if you look at actual Wireshark traces, a numeric string is possible. So if I'm user 100, and I want to set an echo for user 100, the string 100 in ASCII is being transmitted. And this, of course, gives a lot of flexibility. Essentially, you could probably just push sits through this, but it also gives, to me, I've already seen in practice problems where the client and the server didn't agree on the convention how NFSv4 echoes are to be transmitted. But in the end, if you have NFSv4.1 ACLs and you agree on a convention, and if you solve the ID mapping problem, user domain and numeric UID to SID and vice versa, the ACLs are pretty similar. And if you have an SMB server that on server side implements NFSv4 echoes, you will basically have pretty happy users. So what's next? I can't see my file and directory metadata. So there isn't really much significant difference that you can't cover with coding. If you ask for your file info, SMB has a set of info levels where you can just get groups of information, like all info, like just very basic info. NFS is a bit different. You can send it a bitmap, hey, get me this and this and this, essentially a statx call over NFSv4. Both protocols have typical timestamps, file size, and so on, allocation size. Both can do that. Named extended attributes are both there in NFS and SMB. And if you now look at alternate data streams, the way SMB does it is it uses the colon character to distinguish between file name and a stream on that file. And if you really look at the NFS specification, you have a call open named attribute directory. NFSv4 has streams, which is great. I don't know if anybody implements these, but it's optional. But NFSv4.1 has streams, which, yeah, I find kind of cool. It's basically the model that I believe Solaris did back then, that you, on a file handle, you can get a directory handle just listing the streams inside. And from there, you can just open or create alternate data streams or list them. Okay, let's look at this situation where clients or servers die or transport connections are not reliable. SMB basically runs over reliable transport. So we have TCP, we have RDMA, but basically we have QUIC, but these transport guarantee order delivery of packets. But then we got SMB2 multi-channel. And this multi-channel thing was done, as far as I know, for two reasons. First is, of course, performance. And second is that you get better and quicker failover when one of these network connections dies. And so with multi-channel, you have to live with the fact that requests can, or multi-channel enables resending requests over a different connection, meaning that if you decide I sent my create request, creating a file over one connection, and I decide, or I found out this connection has died, I'm able, with the same semantics, or keeping the same semantics, I'm able to resend this over a different transport connection. And the way this happens is that whenever one of these transport connections dies, I increment the channel sequence number, which is like, okay, the world changed. And if I want to now replay a request, I just set the replay bit in the SMB2 header, because the client knows when it's replaying things. The server can't really know, because I will have to indicate to the server that it's replay, because a request from client to server might have not arrived at the server, or the answer might not have arrived. So, and this is why and the client knows whether it sends a request a second time. And so how it does it, it sets a replay in the SMB2 header. And then to replay, create, so the basic modifying requests, or one of the basic modifying requests is create file. So whenever a client wants to open or create a file, it invents a GUID. And so this will then enable the server to actually correctly identify when a client has already or when it already has successfully created a file on behalf of a client, and so reply accordingly. So in the replay header in the SMB2, when I resend the create file, I use, of course, the same create GUID, and the server can then decide, hey, this is the same request sent a second time, and not do all the things like create the file a second time. And essentially, this is a bit of a replay cache that NFS runs with special semantics for the problematic requests. I mean, a read can just easily be replayed, and SMB just deals with this with special handling on the individual requests. Locking calls also can detect replay. They have log sequence number. Oh, numbers. No, it's numbers. It's a typo here. Sorry. Locking calls also can detect that, yes, this has been done before, and the server can just answer with the change locking state from the first attempt. So how does NFS deal with this? For the longest time of its life, UDP used to be a valid transport for NFS. And so NFS, or rather the underlying RPC implementation of ONC RPC, had to implement a duplicate request cache from day one. Because UDP is not reliable, UDP can drop messages, UDP in theory can duplicate messages, and so on. So the NFS server had to have a mechanism from day one to identify duplicate requests. And most of this is based on the 32-bit XID, request ID. In SMB, we call this command number, or it used to be the multiplex ID. And this is basically what it is. But the problem here is that you can read many, many pages in the NFS specifications to correctly identify clients and servers. So clients and servers, to have this duplicate request cache actually work correctly, the server needs to really reliably identify, yes, this request is a duplicate of that request as of 20 seconds ago. And this is up to now, if I read the RFCs and all the discussions right, this is up to now still a problem if you just look at the 32-bit XID and the normal ONC duplicate request cache. Also, there is no real mechanism so far up to NFS 4.0 to correct these throwaway cache entries. How do you, on server side, know that the client has received its response and will not replay this? And there is no way until NFS 4.1. And so NFS 4.1 introduces proper request cache handling. What you do is, as well, the very first, or one of the very first requests in NFSv4 4.1, you essentially allocate an array of request slots on the server, which holds sequence numbers. And whenever a client now chooses or wants to send a request, it chooses a slot number and it sends its current sequence number. That it has a mapping of that array also. And with this request, it chooses a slot number and it sends its view of the sequence numbers. These sequence numbers increment by 1 whenever I send a new request. So the server can know that, oh, client shows slot 5 with sequence number 6, and the last I've seen is slot 5, sequence number 5. This is the indication for the server that the request has, the answer to request number 5 has been received, and it can throw away the answer. And so NFS4.1 is the first protocol in the NFS world that does proper request cache handling. And yeah, this is kind of a difference between NFS and SMB. It's not really semantics at the higher level, like what do we do with logs? It's but it's a very low level difference between those two protocols. Okay, share modes. Now we get to the very interesting and probably a bit problematic aspects. SMB from the beginning was a stateful protocol. NFS was designed as stateless, but SMB was always a stateful protocol. Files have to be opened before they can be used, written to and read from. So when you open a file, you always have some kind of handle to which you can attach logging state. And for single tasking MS-DOS, this was important because MS-DOS didn't expect more than one opener. So one Word.com had to be protected from other Word.com applications when you go into a network. Every application had to be told, yes, you are alone. And the way that was done is just by exclusive share modes. NFS is stateless. And so without any state on client and server, or in particular on the server side, you can't do logging. Then people found out, okay, without any logging, you can't really do reliable file protocols. And so logging was done in external protocols, right, with like state protocols like network log manager protocols and so on. And what happens is that if any of these processes fail, recovery from this failure is still not really a well-solved problem. NFSv4 goes one step beyond that you are completely stateless. And if NFSv4 accepts the fact that you have to add state to the protocol, and NFSv4 adds locking to the protocol itself. NFS, to a much bigger extent than earlier versions of SMB did, deals with client and server failures. And so for locking, a client failure is a bad problem. What happens if a client just dies with logs held? You can't really tell if you are UDP based. You can't really tell when a client died. So very deep in the NFSv4 specification is that these logs and all the state that NFS clients and server agree upon are based on leases, which means that it's not the SMB way of leases. It's the client has to ping in regular intervals to the server that, yes, I'm still here, please keep my logging state. And yeah, that's also, if you read the literatures, that's one of the ways to do logs. If a client dies and doesn't ping the server for like 2 minutes or any amount of time, the logs are just gone. NFSv4 essentially introduces share modes. And in the RFC, you can see, yes, this is to accommodate Win32 clients. However, it's a bit semantically different. So essentially, we have file share read, file share write. We do have that. What we don't have is file share delete. And if you think about this, file share delete is more a lock on the directory entry of a file name. What does it say? File share delete says, please don't remove this file, don't rename this file. And if you look at the Unix file systems, there's only a very loose coupling between a directory entry, which is the name, and the file as such, and this is just the inode number. So in the NFS world, file share delete is pretty hard to implement because you have to lock essentially the directory entry. And to do that properly, you have to lock the directory itself. And yeah, so if we really want to be interoperable on this, we have to look at directory locking and have notification whether whenever a NFS server wants to rename something, we have to look at different locks than NFS natively has to implement. Yeah, byte range locks. I mean, Samba lives in that space from day one. NFS models POSIX byte range locks, SMB models NTFS. I mean, the one main difference is how overlapping locks are handled. But Samba has code for this, thanks to Jeremy, for like 20 years or so. In both protocols, no. In NFS, at least, advisory and mandatory locks are possible. I'm not sure about SMB. However, in the NFS world, read is usually covered by or protected from mandatory locks. So you can usually say, okay, I want to read, but there's a read preventing that read. There's a lock preventing that read. So you get an error message. However, NFS read has a special mode. Hey, I'm super user. I know what I'm doing. Please don't look at the mandatory locks. And that's a protocol element. But I think these can be covered pretty easily. Now coming to the lock state management. And this is really a big difference between SMB and NFS. In SMB, all locking state is tied to a file handle. So you open a file, you lock ranges and so on. And when you close that file, all locking state is gone from your perspective. So it's all really tied to the file handle. NFS is different, and this took me a while, and I hope I got this right. NFS has a completely separate namespace for opens and lock owners as entities, state IDs. So you don't really have a file handle the way we understand the file handle, being a representation of the open. File handles in NFS are really equivalent, I would say, to an inode, a reference to some entity on disk. And you can then have a separate, you can open a file, you get a separate entity that is completely different from the file from what NFS calls the file handle. And you can use this entity in read requests, in write requests. If you then lock a range, you get yet another set of state IDs. And on the next slide, I will talk about delegations. If you acquire a read delegation or a write delegation, that's yet another number space that are essentially completely different. So you have number spaces that can name completely different entities server-side, which are not really tied to, or probably they are in a hierarchy, but they are completely separate. It's not as strictly tied to a file handle as we know it from SMB. So I couldn't find a clear definition of something that is a file handle similar to a POSIX file descriptor. I mean, from my perspective, a SMB file handle is pretty much a POSIX file descriptor, or very, very much equivalent to that. I couldn't find any of this in the NFS spec. This probably was done to implement, to accommodate kernel implementations that can do their own management of logs, their own management of different processes, their own management of different users, and so on. However, it's still unclear to me how we can deal with this in a completely interoperable way between NFS and SMB implementations. So client caching, this is basically naming first. So SMB1 allowed clients to cache via so-called oblocks. And this means that if I open a file with an oblock, I'm permitted to handle requests completely locally, depending on the type of oblock. The point is, oblocks can be broken, but not upgraded while the file is open. SMB2 introduced leases, which is a separate number space, but still tied to a file handle. with SMB2 leases, you can upgrade you can, of course, break leases when other conflicting access is attempted, but you can upgrade a file. You can upgrade a lease while the file is still kept open, and this was not possible with SMB1. SMB2 also allows to cache directory contents with directory leases, and NFSv4 has similar concepts with file and also directory delegations. So if you get a write delegation, essentially what the NFS RFC says, don't bother with talking to the server at all. Only if I break this delegation, you have to, essentially write back your cache state and so on. If you close the file, yes, of course, you have to write this back. So it's a very similar concept. I still have to really digest what this actually means for clients and servers, because to me, and this is, I think, my last slide, to me, the NFS RFC, and what I read was RFC 8881, is extremely hard to understand. Probably I have to implement an NFS server to actually understand this. And that's the end of my slides. And how much time? Yeah, I think it's right on the spot.
Yeah, right on the spot, Volker. Thank you so much for your talk. Do we have any questions from the audience?
I have a question/comment.
Yeah, Tom.
Hi, Tom.
Hi, Volker. There's one thing that always struck me is I know quite a bit about SMB and NFS over the years, but one thing that strikes me that's missing in NFS that's present in SMB that leads to successful extensibility. NFS doesn't do ioctls. FS controls ioctls are all done locally on the client in NFS, whereas SMB sends them to the server. And I find that that's a real key difference in supporting new and slightly different application semantics.
The way I interpreted this was, if you look over the different NFS RFCs, with every single RFC, you get more and more definitions for named attributes. And
named attributes for sure.
Yes, but I think if you just want to extend something, just invent a fresh attribute. You get a file handle, you get a file handle, and you write to extend to a special attribute. You read from a special attribute, and there's your RPC mechanism on that file handle.
I guess.
This is my interpretation of things. They play games with attribute names.
In my opinion, the lack of a clear extensibility mechanism is one thing that sort of freezes NFS in time. That it's very, very difficult. You have to go back to the IETF to change NFS, to do something with NFS. But SMB is much more flexible.
If you look at, I have been pointed at a discussion right now on the NFSv4 mailing lists. Where people ask, okay, we have this protocol element around delegations for 20 years now, and I still have to come across a correct implementation of this.
Yeah.
And so this, I'm not sure how many of these 560 pages are actually being used. And this makes it probably very hard for an NFS implementer to decide what to focus on.
Yeah, in the NFS community, we call this tribal knowledge.
Great. It should be in the docs.
It's not sufficient.
I mean, we would nail Microsoft to the wall over tribal knowledge.
It's a bad thing.
Yeah.
Yep.
And so, I mean, just reading and look at my last slide, you have to implement this, and you have to run against real clients to know what you have to do. And the other way, vice versa as well.
Yep. So, Volker, do you think this, in terms of turning this into code, is this something that will help interoperability between, say, Samba and Ganesha, or?
That's essentially the idea of this exercise.
Right.
So what we need to do very soon is just write tests for this. I mean, just have our SMB torture, and at the same time hammer a NFS server dealing with the same file space. And Windows is one of the obvious candidates here. It does both SMB and NFS, maybe a NetApp.
NetApp is
does it.
Just my guess is that you're going to find CVEs here.
That's tribal knowledge as well, right?
Denial of service CVEs. I am sure of that.
Yeah, but I mean, you have to uncover them. And then just define what should happen when you open a file from SMB without file share delete and you try to remove it from NFS. What is supposed to happen? Are you supposed to wait? Will you get a specific error message? Which one? And so on. So nobody has defined this so far. And you need to...
Jeremy, one thought here. So, I mean, you were saying, write tests and run it against implementation that exists. As you pointed out in your presentation, there's no free and open source implementation available yet. But what about the Microsoft Windows implementation? I mean, we know that newer versions of Windows implement both SMB3 and NFSv4 version 4 servers. So there should be some interoperability here. Can that be used as a reference implementation to test behavior out?
Sure.
I think we probably should.
Yeah, yes, of course. I mean, that's what I said. I have a Windows machine running here with NFS server. Just to test my previous one with symlinks and so on. But I mean, these protocol elements with share modes in particular, does the Windows NFS server do streams? I can only hope so, because I think Ganesha doesn't, and the kernel NFSD probably doesn't either, because there wouldn't be any place to store them. Any further questions? Looking at the chat.
Yeah, Volker, I just dumped my work in progress Git tree there. I started looking into testing the Windows Server implementation for NFS and SMB in parallel. But at the time when I was looking at this, the library that I was using for that purpose, the libnfs library from Ronnie Solberg, was not really sufficiently mature in the sense of supporting Kerberos authentication and things like that. So I think this is really just a start, but for sure we need to invest more into this. So really just not a question, but really definitely
I believe he's fixed that now.
Yeah,
he has done Kerberos. What he has not done is 4.1, and the world has changed with 4.1.
Right.
Anything you want to add to libnfs? I work with Ronnie every day. Just bug me, and I will bug him.
I have that based on T-Event Rec now, because I don't want to deal with that. Okay, I think I'm done here, right?